Good afternoon. Good afternoon, students. Can you see my writing pad? Okay. Thank you. All right. I looked at a few of those that you just turned in, and some of you knew what you're doing. Other of you just absolutely faking it, completely faking it. Wait a second. All right. Now, here's what a couple of you did. A few of you did. Okay. RC equals 1 over omega C. Or the reverse of that as well. Omega C equals 1 over RC. Where did y'all get this from?
First order Lobos filter.
Yeah, so why are you applying to the third order? Why are you applying to the second order? This is true for first order. Huh? A first order Butterworth. It's not true for first order Chebyshev. First order Chebyshev, let's get that. Okay, let me. First order Chebyshev. First order Chebyshev, 1 dB ripple is okay. That's the transfer function. Okay. This is transfer function for first order Chebyshev. 1 dB. Okay. And the transfer function for a first order filter is 1 over RC plus 1 over RC. This is transfer function of first order low pass filter. So clearly for these two to be the same, 1 over RC must be 1.9652. Okay. Or if you want to add omega C in here, okay, S over omega C. So the top one becomes omega C over S plus 1.9652 omega C. Okay. So comparing this to this, 1 over RC equals 1.9652 omega C. So this here, this is not always true. omega C equals 1 over RC. Now, it happens to be true in this case. It happens to be true in this case for the Butterworth, the third order Butterworth, because y'all got a shot of that?
Yes, sir.
All right. Because we have this transfer function. Because we have this transfer function, this splits into two. There's the first order part, and there's the second order part. And so this becomes 1 over S over omega C plus 1 times 1 over S over omega C squared plus S over omega C plus 1. This is the second order part. So this part here is omega C over S plus omega C, okay, times omega C squared, S squared, plus omega C S plus omega C squared. Now this part, some of y'all didn't even give me. Y'all didn't even give me the design of the first order. Well, I'm not saying all of you didn't, because I haven't seen all of you. But this is 1 over RC over S plus 1 over RC. And because this got to be this, omega C is 1 over RC for the first order. That must be true. But also this must be true. K over R squared C squared, okay, S squared plus 3 minus K over RC S plus 1 over R squared C squared. Okay. This must be this. Okay. And because of that, omega C is 1 over RC. But you have to justify that answer. You just can't automatically assume that it's true. You have to go through this process. And one student assumed that was true, and then just pulled K equals 2 out of the air. Some of you are going to lose some marks because of write-up. It's clear that y'all didn't understand what you were doing. Just like you had to design the second order, you had to design the first order. You had to justify that. Okay, you just can't pull these things out of the air. And this must equal this. Any questions about that? All right. While I'm on this, any other questions about the homework? Okay.
I mean, what about the piece-spice part of it?
What about it?
Isn't the cutoff gain? It is supposed to be negative 3 dB.
No. The cutoff gain is supposed to be what? Tell me what the cutoff gain is supposed to be. The cutoff gain is negative 3 dB if the low frequency gain is 0 dB. The cutoff gain is supposed to be negative 3 dB less than the low frequency gain. So the low frequency gain was 6 dB. The low frequency gain was 6 dB. So the cutoff gain should be 3 dB.
Yeah, I saw that.
Yeah,
Well, if
so
I got that and I take it out.
Well,
If you don't want your pressure go, I 2% will mark my way.
say again?
If you don't raise your blood pressure, cheapest, you don't mark my way.
Well, you ain't gonna lose anything by me marking it.
What if, okay, I said in 2 attempts? I know
No. I grade your latest attempt. You can't ask me, you can't send in 2 answers and ask me to choose. Choose the one that's right. I mean, that's nonsense. You even lucky I will accept the second attempt. Some profs say if you send in the first one, that's it. Don't send any more. I will grade the latest that you send me.
If that's the lowest grade, you could drop it, right? Since it was supposed to be makeup, right?
Yes, that's what it said. If this adversely affects your grade, then I won't count it.
All right, no problem.
Yes, sir.
But why y'all don't know that the cutoff frequency is 3 dB less than the low frequency gain? I don't know why y'all don't know that.
I don't know why I thought it would always be a negative 3 dB.
It's always negative 3 dB because the low frequency gain is always 0 dB.
Oh, only at 0.
If the low frequency gain is 0, then 3 dB less than that is negative 3 dB.
Oh, all right. Yeah, I had that at first, but I didn't get them.
Oh, well.
You learn, man, you learn.
Yeah, absolutely. Every wrong answer is an opportunity to learn the right answer. All right. We need to move on to oscillators because you know what? Your final exam is 3 weeks from today. Oscillators. Where do we find oscillators? What does oscillator do? How can y'all go through 243 and even 400 and not know what oscillator is? An oscillator is a device that generates a signal. An oscillator is a device that generates a signal, usually a sine wave, but square wave sometimes, and even a triangular wave. This is what you find in your signal generator in the lab. Your signal generator in the lab is using an oscillator. Okay. So we need to generate sine waves, and an oscillator will do that. Okay, and you have to use oscillators in communication circuits. So you should have seen this. You should have seen oscillators in 243. All right, what do we need for oscillation? How do we generate a sine wave? Okay. Now I want you to cast your mind back to a public event. There's a PA system. The speaker's talking. Okay. And the volume is up too loud, and suddenly it starts to squeal. I'm sure you all heard this at live events. Okay, there's a squealing sound. Well, that squealing sound is a sine wave that's being generated because the signal at the speaker is going back to the microphone in phase, and so we have a positive feedback system. We have a positive feedback system, and that's what causing that sine wave to be generated. Okay. So we need amplifier. Is our amplifier, and I'm gonna put an input here for now. And there's our feedback. And you've seen this You're seeing this circuit, this block diagram. And control theory in 420. What did you all call this block?
G of S.
No.
Is that gain?
What did you call it? I'm
G.
calling it
Is it
A.
gain?
Y'all didn't call it gain in 420. Or if you call it gain,
That's like four.
go ahead.
Like P is like negative feedback of.
No,
Yeah.
this is not negative feedback. I purposely put positive here and positive here. For
That's
this to be
a
negative
feedback.
feedback, this must be negative here. You
That's
must be
a-
subtracting the output from the input. But I'm
positive
not
feedback.
subtracting. This is positive feedback.
So is a loop.
Of course, it's a loop. What did y'all call this part of the negative feedback system?
Yeah, I thought that's the gain.
Did y'all call it G?
G, right? G, like G1, G2.
Well, that's what I'm asking you. What did you call it?
G of
I just
S.
say G of S altogether, right?
Yeah, that's what
You
he
said
called
G of S?
Yeah.
Yeah, he said that.
I didn't hear no of.
That's all.
No, I did not hear of.
No, but I
I
said
heard
that.
G. I
I
heard
said that's why.
GS. I heard GS.
Well,
It's
okay,
not
right.
GS. It's G of S.
Right.
G of S. And what do you call this? What do you call the feedback path? What do you call the transfer function for the feedback?
That's H of S.
H of S.
Yeah.
And what was the overall transfer function? What do you call it, C of S?
You go on output C of S.
All right, you calling this C of S?
Yeah.
And the input's R of S?
R of S, yes.
All right. And so what is C of S divided by R of S?
That's the transfer function.
Yeah, that's the transfer.
No, G of S is not the transfer function. G of S is the transfer function of the forward path. I'm asking, what do you call the overall transfer function? C of S divided by R of S. G of S is not C of S divided by R of S. G of S is C of S divided by E of S. Did y'all call it E? Y'all call the error? What did y'all call C of S? What is C of S divided by R of S?
That's forward path gain.
No, this is not forward path gain. G of S is forward path gain. G of S is forward path.
Yeah, you're trying to look for the
I
name.
am asking you, what is the overall transfer function? C of S divided by R of S. This is the overall transfer function. What is that at one transfer function?
You mean like the closed loop transfer function?
Yes.
That's the closed loop transfer function is you're asking for.
Yes. And what is it equal to?
G of S over 1 plus this G of S times H of S.
Yes. Listen, you may have been trying to say it, but you didn't say it. You did not say it.
What classes come from Dr. Godwin?
This is 420.
Oh,
Man
that's
and
right.
not yet.
This is from 420. No. With positive feedback, this is negative. That's the only difference. This is negative. What do we call G of S times H of S? This is the name for this. What do we call that?
Loop
Open
gain.
loop gain. Yeah, loop gain.
Yes, the open loop gain. So what happens when G of S times H of S? Okay. What happens when that's 1? What happens when this is 1?
If that's 1, that'd be 0. The denominator be 0.
The denominator would be 0. And so the closed loop gain would be infinite. The closed loop gain would be infinite. This is the closed loop gain. Okay. What does it mean to have an infinite gain? It actually means you'll have an output even though there's no input. So in other words, this will oscillate. This will create a signal. This will create a signal if you make the open loop gain, if you make G of S, or in my terminology, I think the book uses A and beta. Let me see if the book uses that. Give me a second.
It is like the same stuff Dr. Turner was saying.
This is exactly it. That's what I've been saying for the past 10 minutes. Except that Dr. Turner looked at negative feedback, and that was positive. I'm looking at positive feedback. Okay. I'm looking at, as a matter of fact, I'm now looking at this going directly back here with no input. And if G of S times H of S, if that's equal to 1, then we have oscillation. And this is called the Blockhausen criterion for oscillation. The Blockhausen criterion for oscillation. Okay. So you want the open loop gain to be 1. Okay. To create an oscillator, you want the open loop gain to be 1. You don't want this in a feedback in a control system, okay? Because then you'll have an output even though there's no input. But you want this in an oscillator. You want this to happen in an oscillator. Okay. Now, so here it is. We call that. Let me. So A is a forward path gain. A is what Dr. Turner would call G of S. Beta is the feedback path transfer function. Okay. The reverse gain. Okay. So A times beta then, A times beta should be 1. That's the Blockhausen criterion for oscillation. All right. So let's look at figure 720. Look at figure 720. This, we could call this the input. We call this the input to G of S. Amplifier 1 times amplifier 2 is G of S. H of S or beta is this times this. Okay. Now the question becomes, what values should A and theta be if we want this thing to oscillate? First of all, okay, let's do that. So let me, oh, yeah. So here I have tan 180, that's a transfer function. Then I have another transfer function, A theta. Okay, that's my G of S. And then my H of S will be the reverse. So coming in here, 1 at negative 135. And then 0.02 at 0 degrees. And then that's fed back into the input. All right. So this output is fed back, is fed through this device, and then this device, and then back to the input. All right. And the question becomes, what must A and theta be for oscillation? So this part here is G of S, H of S. And we've already said, for oscillation, G of S times H of S must be 1. So G of S is 10, 180 times A theta times H of S. H of S is 1, negative 135, 0.020, and that must be equal to 1, 0. That must be equal to 1, 0. So then clearly 10 times 1 times A, okay, times 0.02 must be equal to 1. That's the only way this equation is an equality. The magnitude on the left must be equal to the magnitude on the right. Furthermore, the angle on the left, the angle is 180 plus theta minus 135 plus 0 must be equal to 0. 0 degrees. So from the top, yes, go ahead.
Why do you have the angle sign in front of the 0.02?
Oh, that's an error, sorry. Yeah, that's an error. But it doesn't change these two equations. Okay. So what does that mean then? That means 0.2a must be 1, or a must be 5. Okay, a must be 5. Okay. And theta must be what? Theta must be negative 45. Negative 45. Okay. So if we make a 5 and we make theta negative 45, we will have oscillation in that block diagram. we would create a sine wave. The frequency in which we have A equals 5 and theta equals negative 45, at that frequency, we will have a sine wave created. Any questions about that? Okay. Now tell me something. How are we going to create this? See, it's one thing to see something. It's one thing to see something in a block diagram, and then it's another thing to visualize the circuit that goes with that. What circuit is this? What circuit has transfer function or gain 10 at 180? Wow.
Maybe for a high pass.
Really? First of all, what kind of high pass? Let's go with high pass. What kind of high pass you talking about?
The first order.
Really? So you think a first order high pass filter is going to give you a phase shift of 180 degrees? What's the maximum phase a high pass filter can give you? A first order high pass filter can give you?
You need them all pass.
No. Hold on. Let's answer my question. What is the highest phase a first order filter can give you?
90 degrees.
90 degrees. So that's not a first order high pass filter. What's another way of writing 10 180? What is 10 180 equal to? Ten 180 is the same thing as negative 10. Any number at 180 is a negative number. I'm sure I've told you that a million times. So what block diagram has gain negative 10?
You want to gain a negative 10, you need a non-inverting something.
A non-inverting?
No, inverting for negative 10, for negative gain.
You need the circuit right there. And if this is 10K, this is 100K. That's what you need for that first block. We'll come back to the second. Now we know this is 5 at negative 45. Okay. How do we get this? How do we get a gain of 1 at negative 135? What creates that? What device creates a gain of 1 and an angle, a phase shift of negative 135?
I know that one is have to do some of the all pass.
All pass. All pass. Phase lead or lag?
Slide.
Yes, phase lag. Okay. And you remember that looks like what? What's that look like? That looks like this. Okay. But let me draw it the other way. It looks like this. You come in here. Okay. And you go here. That's the output. Now, what does this look like? What's 0.02 angle 0? What is that equal to? What's 0.02 at angle 0 equal to?
0.02.
Yes. 0.02. So what has a gain of 0.02? What device output is 2% of its input? Because that's how you get a gain of 0.02.
Could I make a guess?
Yes, go ahead.
Would it be a capacitor?
Yeah, man. How does a capacitor have a transfer function? Tell me how a capacitor, where's the input and where's the output?
There isn't any.
This is a transfer function. There's an input right here. There's the input. And there's the output right there. Right? Folks, what's the purpose of a voltage divider? When we create a voltage divider, what are we doing? When we create a voltage divider, what are we doing? We're making the output smaller than the input. What's the transfer function of this voltage divider? What's the transfer function of this voltage divider?
R1 over R2 plus R1.
No.
He said Barcode, I think it was to be R2 over R1 plus R2.
Yes, so we want R2 over R1 plus R2. We want that to be 0.02. That's what we want.
Hold on. So where that's the transfer function right here, right?
This is the transfer function.
Yes.
Yes.
I already just say that though. Just say no.
No, you said R1 divided by R1 plus R2.
It's R2 because you respect the ground. That's why.
I listen very carefully to what students say.
All right, they might have made that mistake for Joe, but that's what I mean. I know.
Listen, I don't grade what you mean. I grade what you say. I grade what you write. I have no way of knowing what you mean. Students, all students mean the right answer after I give the right answer. But they don't mean that before I give the right answer. So, I'm going to solve this. So here's V1. VI will come in here, go here, and V out will go here. So R2 equals R1 plus R2 times 0.02. So 0.98, then 0.98 R2 equals 0.01, 0.02 R1. Or R2. Let me go up here. R2 equals 0.02 over 0.98 times R1. So R2 equals 0.0204 R1. So choose a value for R1. Choose a value for R1. Let's say 10K. R2 then is 2.041 kilo ohms. That's how we create a transfer function of 0.02. And now finally, how do we create this transfer function? How to create 5? How to create gain 5 at negative 45?
Non-inverting.
Yeah, that's it. A non-inverting amplifier gives you what gain? What gain you get from a non-inverting amplifier?
We need to get a gain of 5. A positive gain.
Yeah, what happens to negative 45?
Looks like you need a low pass filter for that.
Well, then if I use a low pass filter for that, if I use a low pass filter for this, what gain is a low pass filter going to give me? A first order low pass filter. What gain is a first order low pass filter going to give me? It's going to give me a gain of 1 over root 2 at negative 45. It's not going to give me a gain of 1 at negative 45. And so if I want overall gain of 5, I need an amplifier that has a gain of 5 times root 2. This would be my non-inverting amp, and this would be my low-pass filter. Because a low-pass filter, when you have a phase shift of negative 45, what is the gain? The gain is 1 over root 2. Okay, I need to hurry now. I really didn't intend to spend so much time on that. But I wanted you to be aware that block diagrams have circuits. And in this stage of your life, you should be able to come up with a circuit.
So Dr. Cartwright, that'll be cascaded or no?
What would be cascaded?
I'm asking the second block diagram. It would be a non-inverting op-amp cascaded with a low-pass filter.
Yes.
All right.
As a matter of fact, all these cascaded. How do I know all these cascaded? These two are cascaded, and these two are cascaded. Because you're multiplying the transfer functions. When you multiply the transfer functions, you cascade the circuit. If you add the transfer functions, you put the circuits in parallel. Okay. Now, here's what I'm going to do. Okay. I am going to use a non-inverting amp and the feedback path. It's going to be this circuit here. Okay, so this will come in here. All right. And this will leave here. Let me redraw that. This is the same thing. This is R and this is C. This is R and this is C. And this is an oscillator called the Wien Bridge oscillator. And this is a non-inverting amp. So it has a gain, it has an angle of 0. Non-inverting amp. Okay. So at the frequency of oscillation, what's the phase shift of this circuit here? What must be the phase shift of this circuit here? This is my H of S. And this is my G of S.
You're asking for the phase shift of H of S?
Yes, what must be the phase of H of S?
Negative
And
135.
huh?
They say negative 135, no it.
Where you get that from, Mr. Buchan? I'm just curious. Where did you get such a figure from? No number from? Besides the circuit we just looked at.
No, I got it from the previous circuit.
But why would you pick on 135, negative 135? Why didn't you pick on negative 45? What is the Blockhausen criterion for oscillation?
Yeah, it is theta equal negative 45.
No, it's not theta equals negative 45. Did y'all not understand anything of I just said earlier today? What must happen for us to have oscillation?
It should be 1 at an angle 0.
What should be 1 at angle 0?
G of S and H of S.
G of S times H of S. You see, you still ain't saying it right. It's not G of S and H of S. You're multiplying those two together. So you're multiplying G of S times H of S. What are you doing to the angles?
So the angle should be the same or 0?
No, that means if one should be negative 45, the next one should be positive 45 for it to be 0.
No. Who said that?
I know, it's oxen.
But where you get 45 from?
I know.
You're pulling 45 out of the air.
So the first angle is 0. The second angle should be 0 as well.
Thank you very much. If we already got an angle of 0, what must the other one be? That must also be 0. Because 0 plus 0 got to equal to 0. The angle of H plus the angle of A or G got to be 0.
So what if it was 45?
What if what was 45?
The angle of A.
Yeah, but it's not. I don't know why we talk about it. It's not. If it's 45, then H should give us negative 45. Yes. But the angle of A, this is a non-inverting amplifier, therefore the angle of A, the angle of A is 0. If the angle of A is 0, that means H of S must be 0. The angle of H of S must be 0. And indeed, if we were to plot the magnitude of H, it'll look like this. If we have time later on in the semester, I will derive this for you. And this happens at 1 over RC. This happens at 1 over RC. We have a magnitude. We have an angle of 1 over RC. This is omega. And the phase looks like this. The phase looks like this. This is 0 degrees. And this is 90 degrees. And this is negative 90 degrees. And at this frequency that we have at 1 over RC, that we have a phase shift of 0 degrees, that's what we're interested in. So if this thing's going to oscillate, it's going to oscillate at 1 over RC. Okay. Now, that is not enough to say that we're going to have oscillation. Okay. We need two things for oscillation. We need the phase to be right, and we need A to be right. Now, how are we going to find out what A is? What do we need from A? Well, when we have a phase shift of 0 degrees, when we have a phase shift of 0 degrees, we have a magnitude of a third. So the magnitude of H is a third. So what must be the magnitude of A? Keep in mind the Barkhausen criterion for oscillation.
So that should be 3.
Should be 3, yes. You always go back to the Barkhausen criterion for oscillation. GH, G of S times H of S must be 1 at angle 0. So that means the magnitude of H times the magnitude of A must be 1. I just told you this is the third. Okay. So we must have 3. A must be 3. And how do we create a non-inverting amplifier with gain 3?
That means the RF should be 2 times greater than RI.
Talking fool, Mr. Beauchamp.
Again?
Talking fool.
What and the formula is 1 plus for the gain, and it's 1 plus RF over RI.
And then plus 1.
Yeah, plus 1 again.
Sorry, what did you say, Mr. Beauchamp? What did you say?
I'm asking if the gain, you say non-inverting, right?
Yes?
And it's 1 plus RF over RI.
Yes.
So
Yeah, finish what did you say earlier?
that's why I said earlier RF should be 2 times greater than RI.
Yes.
That's what they say, and you say nonsense.
Well, that's why I'm checking again to see whether or not I heard you correctly the first time.
Yeah, that was my statement. RF is 2 times greater than RI.
All right. So, what we got now then? What circuit do we have? You see, this ain't a circuit yet.
Let me get a picture of that very quick. All right, I get it.
Okay. This ain't a circuit yet. This is a circuit, but this ain't a circuit. That's a block diagram. So this is a Wien bridge oscillator. I should say basic Wien bridge oscillator. And note, this R does not have to be the same as that R. Some of y'all made that same mistake on the homework you just turned in. Well, it's not a mistake. But when you make this equal to that, and that's what a lot of y'all did, there was no need for that. The gain determined resistors are different from the frequency of the sine wave determining resistors. All right.
But they could have been the same, right? Daughter got it.
Yes.
Could have still have been the same thing.
Yes. But they didn't have to be the same. That's my point. This got to be twice whatever this is. And those values are totally unrelated with these values. Totally unrelated. All right.
Hold on. In the homework, the feedback resistor was in twice Ri.
No, it was the
hold on.
same
Yeah.
because you needed a gain of 2. And by the way, some of you all just told me I need a gain of 2, and you didn't tell me where they came from. Well, you don't get credit for magic in your write-up. You don't just pull a number out of the air. All right. Now, let me tell you what the problem with this is. If you have the gain exactly 3 in the real world now, I'm talking about the real world. This may not oscillate. You actually have to go a little above 3. This starts to oscillate, okay? And then what may happen, so you starting off here, you gain slightly more than 3, it starts to oscillate, it'll grow, and then it may saturate. It may saturate. Okay. So we don't want that to happen. So what we need to do is have the gain a little bit bigger than 3. And then when it starts to grow, we want to decrease the gain below 3. Okay. So what will happen then? The amplitude will go slightly beyond that what you get with a gain of 3. Okay. And then when you decrease it, the sine wave decreases a little bit. Okay. And then when the sine wave decreases, you have to gain 1 to 3, and the sine wave increases. So that overall the sine wave looks like this, but this gain is changing as the waveform changes. Now, let me show you the circuit so you can better see what I mean, what I'm talking about. Let me get the students. Greenbridge. Okay. All right. Do you see what we've done? What have I done? Can you tell what I've done?
I see you add a whole other circuit by the feedback loop.
All right. So what's the gain? What's the gain of this circuit? What's the gain of the op-amp circuit?
$1.8.
How you get that?
3.28.
How you get that?
Wouldn't his RF be 18K and his RI 10K?
Really? How do you get the gain? How do you get RF to be 18K? What's your logic? What's your logic in saying that?
I don't really know.
Yeah, you didn't use any logic. You see R3 where you think RF should go, but that's not where RF should go. Where does RF go? RF goes from this output back to here. What resistor goes from here to here? Well, that's R3, and that's 3K if the diodes are off, right? If the diodes are off, you realize diodes are either on or off in a circuit, right? I mean, you know that much from 230. So let's assume D1 and D2 are off. Okay. RF is 21K. Everybody see that? If D1 and D2 are off, then they're open. And if D1 and D2 are open, R2 is not connected to the circuit.
So you just add an extra 0.1 to the overall.
I added 0.1. So what? So the gain is now how much? How much is the gain?
3.1.
3.1. So the gain is slightly more. The gain is slightly more than what we need. Okay. So oscillation will begin. Oscillation will begin. Okay. Now, when it begins, it will. The gain is more than we need, so the output will be saturated. We'll try to go and be saturated, and so as the gain increases, let me show you down here. So we got two voltages here. The bigger voltage is the output voltage, and the smaller voltage here is the input. Is the input to the op amp or the output of H of S, and of course that should be a third. That should be roughly a third. Why? Because the gain here is 3, so the output is 3 times the input. So see what happens here. The input climbs and it climbs and climbs until it starts to reach a plateau. Okay, but before it can reach a plateau, the diodes kick on. The diodes kick on. Okay, so this bottom one kicks on the positive half cycle, and top one kicks on in the negative half cycle. And when the diodes kick on, what's the gain of the op amp? When the diodes kick on, what's the gain of the op amp?
3.2.
No. Where do you get 3.2 from?
I thought the R2 would have been connected.
R2 is connected. When the diodes are on, R2 is not connected. But if R2 is connected, what's the gain?
Is R2 in parallel with R4?
Very good, young man. R2 is in parallel to R4. So 1K and 3K in parallel is how much? What's 1K and 3K in parallel?
750.
750 apples.
Ohms, sorry.
750 ohms. So, what's the gain?
You're getting 2.875.
Exactly. 2.875, which means what? The gain is less than we need for oscillation. So what's going to happen then? The oscillation is going to start to decrease. Okay? The oscillation starts to decrease. Why? Because the gain of the op amp is lower than 3. Okay. And then when the output starts to decrease, okay, the diodes kick on again. Sorry, when the gain starts to decrease, the output decreases, and the diodes are now off, which means the gain is now 3.1, which means the output increases. And in that way, we stop. And this repeats over every cycle. That way, we stop saturation from happening. And we got a fairly decent sine wave. And then we take FFT of that. It's the FFT of that. So what does this show? We take the FFT of that waveform, well, both waveforms. The top one is the output, the bottom one's the feedback. Okay. What we see? We got a frequency of what? We got a frequency of 900 hertz. 900 hertz. That tells us we have a sine wave of 900 hertz. And there's a little bump here. There's a little bump here, which means it's a little sine wave here, but it's hard to see it. So there's a little bit of second harmonic distortion. And what was his original? Yeah, he wanted to design 900 hertz. He wanted to design 900 hertz, and he got it pretty good. Okay. Now, do you all see? Do you all see your assignment?
So what made you choose these two resistor values for R2 and R4?
We just need, they're not critical. They're not critical. All we need to achieve is a gain slightly more than 3, so oscillation will start. Let me tell you, back in 1953, I think this circuit was first invented. In 1953, they had a light bulb here. They had a light bulb here because when the light bulb, when the circuit was off and you first turned it on, the light bulb resistance was low. And then when the light bulb heated up, resistance went higher. So you had the low resistance, not in this configuration, but in a configuration that would make the gain. When the light bulb was off, the gain was very high. And when the light bulb came on, the gain was low. Okay, so anytime you have a Wein-Bridge oscillator, you need some way of regulating the gain. Okay, so that you have higher gain for oscillation to begin. And then you lower the gain as the signal continues to oscillate. All right. Do you notice anything else here? You notice anything else in this circuit? Let me point out this capacitor. What do you see about capacitor 1?
I see your IC.
What does IC mean?
Is it a coupler?
No. IC means initial condition. IC means initial condition. IC means that's the initial voltage cross capacitor. In the real world, you don't need initial voltage on the capacitor. Why? Because there's noise in every real world circuit. There is noise in every real world circuit, so that in the real world, you'll amplify that noise and you'll start oscillation. In PSpice, that's not true. In PSpice, there's no noise. So you have to create an initial noise to get the oscillation moving. So I put an initial condition across that capacitor. 1 volt across that capacitor. There's 1 volt At time t equals 0, there's 1 volt across this capacitor.
Question, Dr. Cartwright.
Yes?
Can I put like a potentiometer at R4 to like control the gain?
You want to be there all day controlling the game?
This is wondering.
Well, that's the reason why you don't do that. Because you don't want to be there operating the signal generator and not being able to do anything else with the circuit, with another circuit. You want this done automatically. And if you look in the textbook will do it another way. And usually, if I have time, I explain what the textbook is doing. Yes. Anybody see how the textbooks were doing it? Anybody recognize this circuit right here? This diode, this R and this C, anybody recognize that circuit? I think we teach you these circuits and y'all just learn it to pass the exam and then forget about them. You first saw this circuit in ELT 111. This circuit here is a half-wave rectifier. This circuit here is a half-wave rectifier. So at the gate of this field effect transistor, we have a voltage, a DC voltage proportional to the amplitude of the output of the circuit. When that voltage goes high, the resistance between the drain and the source, in other words, that's Ri, isn't it? Okay, that's Ri. The resistance between the drain and the source is Ri. That value is low. Okay, when this voltage is low, okay, so that the gain is high to begin with, and when the oscillation builds up, there's a DC voltage here that's now higher, and that DC voltage is higher, causes the drain to source resistance, okay, to be larger. So now RF of Ri, okay, is smaller, and the gain goes down. We call this an automatic control, automatic gain control circuit. Okay, that's another way of doing it. The point being, any real world Wein-Bridge oscillator circuit must have a way of controlling the gain. Okay. All right. I hope everybody got a snip of that. So this is your next assignment. This is going to be due for Wednesday at 11:45. You're gonna design a circuit, a Wein-Bridge oscillator, so that it oscillates at n times 100. N times 100, where n is your number, hertz.
Dr. Carter, you can send that via email.
Well, I could, but I don't know why I have to.
Please do.
I'm just asking you to design a Wein-Bridge oscillator, as you see here. with an oscillation frequency of
So
n
we have-
times. Go ahead.
So class on Wednesday as well.
Yes. You can have Monday off.
Or the guy, you gonna make this do on Friday?
Why?
Yeah, it's an extra dime, eh? This,
Yeah, but I spoiled you all semester.
all right.
This would be our last assignment, correct?
Why?
You mean me, Dr. Carrick?
Say again?
I asked if this would be our last assignment.
And I say, why do you say that?
Because looking at the time, 3 weeks till the final. That's why.
I haven't decided if this is the last or not.
All right.
This an next makeup one.
Yeah, I guess it could be. And also, I want you to give me the spectrum, as you see here. You get that by using the FFT button. See, his design value was 884. That was his design. Okay. That was his design. And his actual is 900. It's measured as 900. Because that's where you have the peak. You have the peak right up here. Okay. Okay. I'll send out this assignment. But in the meantime, you get started.
You scroll back
Yes,
up, please, Dr. Drake.
To here?
Yeah, right there. Thanks.
Okay, okay, we don't have 9 students in our class, so I'm good. I'd be showing you the design right here. But I'm good. Okay. The highest we go up to is 800 hertz. Okay. Any questions, any concerns? See you all on Wednesday.